Shell type transformers. This is shell type transformers. So features of the shell type transformers: windings encircles the core. So these are the windings which encircles the core. Two magnetic circuits. Here, unless in a core type transformer there are two magnetic circuits, because of its construction, windings encircles the core. So two magnetic circuits are provided here. Two magnetic circuits will be there. Preferred for high power transformers where voltage rating is greater than 11 kilovolts. But in core type transformer that is preferred for low voltage transformers, but here the shell type transformers are preferred for high voltage transformers. Core is made from stacking silicon steel laminations as core type transformers to reduce hysteresis and eddy current loss. Each lamination is coated with varnish to provide insulation. So here also each coating, see here the very thin laminations, very thin in terms of laminations, these are coated with varnish to provide insulation. So each laminations are insulated from each other. So while it has been staggered, when it has been compressed together to form this much thickness core, so when laminations has been insulated from each other. Each lamination are insulated from each other to reduce hysteresis or eddy current loss. Windings are made from copper or aluminium. Once again the same thing here. The windings are made from aluminium or copper. But if you use copper, you get very good is a very good conductor. So better use copper instead of aluminium. So difference between core type and shell type transformers. So here is the core type, here is the shell type. The windings encircles the core in a core type, but in a shell type, the core encircles most part of the winding. In the core type, only single magnetic circuit will be there, but in shell type, dual magnetic circuits will be there. Core has two limbs, but here core has three limbs. In shell type, core has three limbs. So what is meant by limb here? So this is one limb, so this is second limb, this is the third limb. So in a shell type transformers there are three limbs, but in a core type transformer there are only two limbs. These are the limbs. These are the transformer limbs, and this is called the core. The outer portion of a transformer is called as core, and these are called the limbs. So core type has got only two limbs, but shell type has got three limbs. Here core type cylindrical coils are used, sandwiched coils are used. So what is meant sandwiched? Here primary and secondary are placed one over the other, just like a sandwiched. So they are sandwiched, but they are perfectly insulated from each other. They will never touch each other, but they are kept as a sandwich type of coils. So natural cooling is effective. Here natural cooling does not exist in a shell type transformer. So natural cooling will not be provided. Each transformer, when it is operating, the cooling it has to be provided, but in core type transformer natural cooling can be done, but in a shell type transformer natural cooling cannot be possible. Coils can be easily removed when there is any repair comes or any fault comes. In a core type transformer, the coils, the windings can easily be removed, but because of the sandwich type of coils in a shell type transformer, very difficult to remove the coils. So there is the biggest disadvantage of shell type transformers. So core type is preferred for low voltage transformers, and shell type is preferred for high voltage transformers. Losses in transformers. There are mainly two losses in a transformer. One is core loss, second is copper loss. The core loss is also called as constant loss, and copper loss is called as variable losses. Core loss or iron loss, it can also be called as iron loss. So there are two types, hysteresis and eddy current loss. There are two types of iron loss or core loss. One is hysteresis loss, second one is eddy current loss. Iron loss is a constant and does not vary with load. It will not depend upon the load. Each time the magnetic field is reversed, a small amount of energy is lost due to hysteresis within the core. So we know that when the primary current is applied to the primary of a transformer, a magnetic flux is created. This flux which will move in the core of a transformer. So it will travel, it will go in a core of a transformer. So each time when magnetic field is reversed, because in a transformer when a magnetic field is created, each time when it is reversing, a small amount of energy is losing, so because of the hysteresis loss. So this is determined by conducting no load test or open circuit test. So this is called hysteresis loss. When alternating current flows through the windings, the core material undergoes a cycle of magnetization and demagnetization. So because of this, a hysteresis loss will take place because it takes in the core of a transformer. So it is called a small amount of losses in the flux as well as current. It is called as hysteresis loss because of number of cycles of magnetization and demagnetization. It is given by hysteresis loss given by kh bm to the power 1.6 FV watts, where kh is equal to hysteresis coefficient, whose value depends upon the material, which material we are using for a coil or a core, and kh is equal to 0.025 for cast steel and 0.001 for silicon steel. So also depends upon the which type of core material that you are using. Bm is a maximum value of flux density, that is in Tesla. F is the supply frequency. V is equal to not voltage, it is the volume of the core. So total it is called in terms of watts. It is the unit of this hysteresis loss is in terms of watts. So high silicon content in the core minimizes the hysteresis loss. So if you use high silicon content in the core while doing for laminations, then hysteresis loss can be minimized. Next is eddy current loss. The eddy current loss is a complex function of a square of supply frequency and the thickness, square of thickness of the material. So that means to say, so supply frequency and thickness, it varies as a square as well as it varies as the maximum value of flux density. So eddy current loss, it is given by Ke Bm square F square T square into V watts. Once again, V is the volume of the core, T is equal to thickness of lamination, that is in terms of thickness, maybe in terms of mm. So F is equal to supply frequency, Bm is the maximum value of flux density, and Ke is the eddy current constant. By laminating the core, eddy current loss can be minimized. So that is one hint has been given. To minimize the eddy current loss, we need to laminate the core. Next comes copper loss. Current flowing through the winding causes a resistive power loss because current is flowing when primary is supplied with the voltage. Primary current is flowing through the primary winding of a transformer. Secondary current, when the load has been connected to the secondary of a transformer, secondary current flows through the secondary coil of a transformer. When both current are flowing in both the coils, definitely there is a power loss. It is called as I1 square into R1 and I2 square into R2. Total it will create copper loss because current flowing in the copper windings of a transformers, so it creates copper loss. It varies as the square of the load current. That is very important because if you see the formula, that is I1 square and I2 square, so it varies as the square of the load current. Losses can be determined by conducting short circuit test. So this copper loss can be determined by conducting short circuit test. Next, voltage regulation. It is defined as the change in its secondary terminal voltage from no load to full load, expressed as the percentage of secondary terminal voltage at no load, where the primary voltage being assumed constant. See, you can observe in the formula secondary no load voltage minus secondary full load voltage divided by secondary no load voltage. So defined as the change in secondary terminal voltage from no load to full load. So that means to say, when there is no load, what is the secondary terminal voltage? When there is a full load, what is the secondary terminal voltage? Expressed as the percentage of secondary terminal voltage on no load. So no load secondary voltage, full load secondary voltage divided by no load secondary voltage. So that is called voltage regulation of a transformer. Significance of voltage regulation. Ideally, regulation should be zero. So if the transformer is said to be very good transformer, then ideal transformer, its regulation should be 0, but the ideal transformer which will not exist in the world, so there will be always a regulation in transformer, but the regulation, a practical transformer should be less than 5%, then it is called as a very good transformer. It has been given here, typically a regulation of a practical transformer should be less than 5%. So what is my regulation? There is no regulation in secondary terminal voltage from no load to full load. If there is no variation from the secondary terminal voltage, so secondary terminal voltage from no load to full load, if there is no that much significance change in the secondary terminal voltage, then its regulation will be very less. Variation in the secondary terminal voltage is due to voltage drop in the primary and secondary windings. Why this voltage regulation will come? Because of the secondary terminal voltage variation. Why the secondary terminal voltage variation is coming? Because of the voltage drop in the primary and secondary winding. When the current starts flowing in the primary and secondary winding, so there is a voltage drop. There is a significant voltage drop in the primary and secondary winding. Because of this, voltage regulation will increase. The transformer with the low impedance will have very good regulation. So there is one hint has been given. The transformer with the low impedance will have very good regulation. So that's about the voltage regulation.